And with that blank piece of notebook paper, I need you to cut it and tear it into 16 squares. Okay? 16 squares of relatively the same shape and size if you can. It doesn't have to be perfect, but I want 16 squares. Again, you should have 12 scraps of paper that say W and 4 scraps of paper that say L. Finish it up while I kind of outline what we're going to do. 12 W, 4 L. This is back when they're good, so you should be happy about that.
I just saw it and I was like, oh, this isn't.
All right. Actually, this is now relevant again, by the way. There's been a lot of talk about getting another NFL team in Los Angeles. That actually is relevant. There's actually talk about that again. If you were an owner of an NFL team, you might ask the question, would we have home field advantage by moving our team to LA? Because we know that in the real world of athletics and sports at the professional level, you get more money if you win more games. To investigate this question, let's look at available data from a team that played in LA. One of the last teams to play in LA was the 1985 Raiders. Before they moved back to Oakland, that 1985 Raiders team had 12 wins and 4 losses. Here's the catch. At home, they were awesome. They were 7-1. On the road, they were 5-3. Okay? The difference in their winning percentage at home and on the road is this. Their winning percentage at home. Do you agree that that is 7 out of 8 games? And I can calculate that as a percent. Yeah. By the way, 7 divided by 8 is 87.5. Their winning percentage on the road, they won 5 games out of 8. 5 out of 8 comes to be 62.5%. If I want to compare the differences of home field versus away, it should make sense that I'll subtract those numbers together. And that'll tell me whether or not home field advantage is actually a thing or not. Does that make sense? If I win 50%, if I have the same percent away and at home, do you agree when I subtract them I'm going to get a 0? When I subtract them and get 0, do you agree that that means there's no difference between home and away? Okay? A positive difference, in this case, a positive difference of 25%. I won 25% more of the time at home than I did away, according to this 1985 data from the Raiders. Is everybody okay with that? Yeah. Okay? So, here's the question that I want to ask. And here's what we're going to run a simulation of. Does this difference of 25% give me evidence to say that I should move a team to LA because it looks like they're winning at home a lot more frequently, and I know that if they're winning a lot more at home more frequently, I'm going to be more successful and I'm going to get more money as the owner. So is this something to go ahead and move for? Okay? Does everybody understand the question that we're talking about here? Yes? Okay. So, here's how we're going to simulate that. You guys are, oops, that's the next example. You guys are going to take your papers. What you have in front of you is that Raiders schedule with their records. 12 wins, 4 losses. You guys have already figured that out. I have 16 games. They played a 16-game season. Here's what I want you to do right now. I want you to take your papers that you have, mix them up, shuffle them as best you can. We are going to make them in the biggest variety we can whatsoever. You're not looking at them. You are just shuffling them up, putting them in the most random order that you can get them in. Okay? Once you get them in the most random order that you can get them in, I want you to make sure all the letters are facing down. All the letters are facing down. So now you've shuffled up your papers, right? All of your letters are facing down. Now here's what I want you to do. Get them in one little pile for you. Give them in one little pile. And pass your stack, your deck, to the person on your left. Pass your deck to the person on the left. Don't look at their numbers yet. They should just be face down. You can't see anything. And hope you'll agree with me right now. You've got a shuffled deck of 12 and 4 in front of you. It's as random as the person previously could make it. Now here's what I want you to do. Right now, with your new set of cards, make 2 piles of 8. Make 2 piles of 8.
Anyway.
2 piles of 8, any way you want to make it. 2 piles of 8, any way you want to make it. All right. You should have 2 piles of 8. Are you with me so far that this is pretty much kind of as random as we can make it in the context of this classroom? Yeah. Okay. The pile that is closest to me, I want you to pick that pile up right now. If you don't have a pile that's closest to me, then I want you to pick the pile that's closest to your belly button. Okay? You should be able to, are they even?
Yeah.
Then go with this. If you don't have a pile that's closest to me, go with the pile that's your dominant hand. That is fine. All right. So do we have a random pile? Yes. It's pretty arbitrary with what pile we pick right now. Essentially, we flipped a coin. Okay? So you've got this mixed up random. That pile that you have in your head, hand, foot, head, shoulders, knees, and toes. That pile of paper that you have, there is 8 pieces of paper in there. 8. 4 and 4. That is 8 pieces of paper. That pile in your hand is your simulation of your home games. Now I want you to look at your home season record right now. So take that out on a separate sheet of paper. I want you to write your win-loss record at home. Your win and loss record at home. Okay? Again, you need to have your win-loss record at home, and I want your winning percentage at home. Your winning percentage at home is the number of wins divided by 8. Okay? Once you've done that for home, I want you to do the exact same thing with your other 8 games. Your other 8 games is your away win-loss record on simulation.
I beat you guys. Look at all this winning, except at home where I suck. I'm more of a winner. Yeah.
Yeah. You should have 2 percentages. Your home winning percentage, and your away winning percentage. You need to have.
It's okay that I had like 5 out of 3 out of 8 and 10 or away.
Okay. Does everybody have those 2 percentages? Home and away. Now, I want you to subtract. We're looking for the advantage at home. So you will start with your home winning percentage. Some of you guys did really well at home. Some of you guys did really bad at home. Okay? Some of you guys are the same. It's almost like this is supposed to work this way. So, what I need you to do is take your home winning percentage and subtract out your away winning percentage. Home minus away. After you have, it can be negative. A negative percentage means you actually had a better win-loss away. That's a negative percentage. A positive percentage means you actually had a better win-loss at home. A 0 percentage means there's no difference whether you played at home or away. In other words, you have the exact same record at both places. Okay? So, here's what I want you to do. Once you have your percent, I want you to come up here and plot it as a dot plot on the board. One at a time.
You should have done flowers or stars.
Hey, look at us. You guys do that also? Yeah. Just here.
I shuffled fabulously, didn't I, Jay? Yes.
I don't like that.
Okay, you know what? There's nobody else is positive.
That would be
There's only certain possibilities that happen.
That means
We're not going to go into that.
Everybody's going to either end up with one of the numbers that I have.
Why wouldn't people win at home? It should be possible.
What's that? We can get to 50%. It just didn't happen in this simulation. These are the lowest you can get. These are the only 4 outcomes. 5 outcomes.
I want to know the chance of us not getting that. Nobody moves.
Well, here's a thought. We have to pick the one closest to it.
Took you a while there, Diego. There you go.
All right. I think there's about 35 people in class. Okay? Ish, somewhere near there. That represents, hopefully, you'll agree with me, a simulated season for each one of you. There's 35 simulated seasons there. There's 35 people in class. I don't know how many there is. Now, this was based on this big assumption. My assumption in my simulation was there's no difference between home and away. Right? Didn't I say pretty much randomize it as best you can? We know we were up 112 and 112, lost 4. And I said, let's assume that there's no difference whatsoever between home and away. What's the probability you're going to end up with that 12 and 4 record? This is what you guys came up with when we had that 12 and 4 record. Now, the 1985, 84, 85 Raiders said that 25%, that owner was ready to move to LA. That's a big difference. I win a lot more at home. If home field doesn't have an advantage, and it's just random and chance that you're winning at home versus winning away, doesn't that Raiders season fall right here in terms of a simulation with no difference? So now my question is, that 25% difference between winning and losing significant? Not so much. It could have been random chance. Okay? So that's what simulation does for us. In fact, we just need to move a couple things. If these guys happen to be maybe here, what does that start to look like? And shouldn't this data, when we simulate it, be centered around 0 if we said there's no difference between home and away? Okay. So, and again, law of large numbers. This was only 35. We happen to end up with data that looked like this. If I had us run it 3 more times a piece, so we get close to 100 data points up here, do you think this would start to take on a little bit more of that normal? And that should make sense. So our simulation says there's no difference. That 25%, That'll occur pretty frequently when it's random. So our conclusions say, no, based on this, your team was just good that year. It didn't really matter if they played at home or away. They were just good. Okay? That's what we're doing simulation. Next part, let's go ahead and quantify. Do you have a good idea of how that's working out as we see how that fits? Okay? That's one way we're going to use simulation. Another way we're going to use simulation. I'm bringing drugs back into it today. Apparently it's a very druggy day. If a car is stopped for speeding, the probability that the driver has illegal drugs hidden in the car is 0.14. A police officer manning a speed trap plans to thoroughly search cars he stops for speeding until he finds one with illegal drugs. Okay? So that's what this cop's doing. He's only sitting there trafficking for a speed trap. After he pulls you over, he's going to search your car. And if you don't have drugs in your car, he's going to write you the ticket. You're going to go. And then if you have drugs on your car, he's going to stop probably because it's going to take him the rest of the day to deal with that. So here's what we're going to do. We're going to use simulation, and this is how we're going to use it to estimate a probability. Use simulation to estimate the probability that illegal drugs will turn up before he stops the 10th car. We know overall, of the cars he stops, 14% of the cars have the drugs on them. But the probability that I want to estimate here is what's the probability that I actually find drugs before the 10th car? Because we know 14 times out of 100, does that make sense on average? I should find a car with drugs? Which is a little bit more than 1 out of 10, isn't it? In fact, isn't it technically 1.4 cars out of 10 I should find drugs on? That really kind of makes sense of that, kind of moving the decimal around? Okay, so here's how I'm going to simulate that. And it says before the 10th car. That means I can stop up to how many cars? Before the 10th car. 9. Okay? This is kind of the tricky part of simulation. We're going to design simulation. What you need to do in simulation is, again, use the idea of randomness. We're going to go to this random number table. We're going to use our calculators. I'll show you how to use a random number table. The random number table first. It is in the back of your textbook, the random number table. It just says random number table. I don't know what page it's on for sure. But it's back there. It's just a big set of pages. I just don't want that. That has numbers as random as we can get them in the real world. Okay, and there's some other stuff that goes about non-random stuff that's really kind of beyond this course. But we're looking at just sets of numbers digits between 0 and 9. Do we agree that there's 10 numbers between 0 and 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9? It's 10 digits. Okay? So, and each digit has an equal likely chance of being chosen. 8. That next number 4, equally likely could have been 8. Could have been any one of those 10. The way that I kind of visualize for this random number table, I've got the 10 ping pong balls like from the lottery going on in my little magic bucket over here. I pick out a number, I look at that number, I write it down, I put that ball back in the hopper, it spins around for a while, and it spits out another ball. Okay? So these numbers are as random as we can make them. How are we going to do it? We got to make some rules using the random numbers. So first off, I'm going to start with the probability of 14%. Okay? They told us there's a probability of 14% of it being on drugs. The drugs in the car. Not the car being on drugs. All right. So I've got to find some way that I'm going to relate these ideas. And here's what I'm going to do. I'm going to say, let the numbers 0, 1 through 1, 4 equal a car with drugs. And then that's going to be the numbers 15 through, and I'm going to write 0, 0. Are we okay with that? 15 through 100, basically. There's going to be a car without drugs. Are we okay with me translating from the 14% to what I have here? All right? Now I'm going to define it a little bit more. I'm going to let a random 2-digit number represent ENT, a car that is pulled over by the officer. OFSC or ER for officer. ER?
CER.
CER? There we go. So that if I'm looking at my random number table right now, the first 2 digits that I see in my random number table are the number 84. That would represent a car that I pulled over for speeding, but when I searched it, it did not have drugs. Does that make sense? Okay? So I've kind of defined, I'm using random numbers to simulate that probability. That's where I'm getting the 14 and the not drugs. Okay? Now here's my trial, or my simulation. It says I'm going to simulate 10 times. I want to simulate 10 times. A simulation will end when I have stopped 9 cars without drugs, or I find a car with drugs. Because we're looking for the probability that he finds drugs before the 10th car. So that means I can go 9 cars without drugs, or I can find drugs before the 9th car. Yo.
Is this all in the scheme or something?
I'm not using that. I'm just using. This is scheme. If you want to relate it to those themes, this is I think what's the top part probability. Scheme is everything that I'm doing right now. Stopping rule. That's what I'm talking about right now. 9 cars without drugs versus a car with drugs. I think it's easier. I used to put those in. The students try to memorize those things. I think it's easier just to come up with something and simulate it. So I kind of end up pulling that out. That's what's not on here. Okay? So we're going to simulate this thing 10 times at the end to calculate this probability. So I'll finish it. Probability will be the number of cars, number of times drugs are found, bless you, divided by 10. Okay? So that's described exactly what I'm doing in this simulation. Okay? Using the random numbers to figure out if there's drugs in a car or not. It said the probability before 9 cars. So that means I'm going to search up to 9 cars, or I'm going to stop searching after I find drugs, because that's what this problem said I'm going to do. Okay? So let's look at our first simulation. I'm going to read from left to right. 84. Does that car have drugs or no?
No. No.
No drugs. 17.
No.
No. 70. No. 67. 57. 17. 61. 31. 55. Isn't that 9? 1, 2, 3, 4, 5, 6, 7, 8, 9. I pulled over 9 cars. I didn't find drugs. That's the end of my first simulation. So I'll just kind of write right here, S1 stands for simulation 1. Do we agree that that was no drugs? Does that make sense? In other words, I just simulated a cop stopping 9 people. I searched every one of those cars, didn't find any drugs on it. Make sense? Okay. Now we're going to start simulation number 2. 82, 51, 50, 68, 14.
Yes.
All right. That's the end of simulation number 2. I found a car. Simulation number 3. Here we go. Yes or no?
No.
41,
No.
5,
Yes.
simulation number 4. Done, yes. That was, what's the Niners guy who just got popped? Who's the Niners dude up there? Yeah, Olsen. He got caught at, what's like 7 in the morning? He got popped for his DUI, I think, something like that. 7 in the morning.
Yeah.
7 in the morning. Yeah, well, he's had multiples, but when you get popped for a DUI at 7 in the morning, both of those situations don't end good. Either you're still up from the night before, partying, or you woke up that morning and are that drunk by 7 a.m. Neither one of those are good things. Especially if you're a professional athlete that has a game on Sunday. All right, next one. 20 is a no, 31 is a no, 6 is a
Yes.
What is with everyone on the street?
I don't know. Anybody watch Brooklyn Nine-Nine? 44,
No.
90,
No.
50, 59. Oh, we're going somewhere now. 59, 88, 43. Is that 9? 1, 2, 3, 4, 5, 6, 7.
How much simulations you No, use red. Yeah. Well, you're already doing right now.
I think I already screwed up that. No, yes. Do we see the patterning? All right, do we understand how I'm running the simulation now? Okay, we're supposed to do 10. I will tell you that for simulation for 8, 9, and 10, they all have drugs. Okay? I'm going to save you guys some time. I'm going to tell you how this story ends. 8 through 10. 8 doesn't? I'm pretty sure it does.
Yeah, it does.
I think they all do.
It does. 7, 8, right on the 9.
Okay. Okay. This problem originally asked us, estimate the probability that they find illegal drugs before he stops the 10th car. Probability, success over total. How many times out of 10 did I find drugs in the car? 9 times out of 10. So my probability will be 0.9.
All we do is talk about drugs.
We're doing drugs.
That's my life every day.
Is there going to be video tonight?
Is that?
Is there a video tonight?
Yeah.
Is it up yet?
Nope. I'm recording it after school.
So it'll be up at 5 last week?
Yeah.
You know, say day 4.
Day 4 boot camp. It'll be graphing, polynomials.
That sounds awful.
Okay.
Oh, easy
Oh
mode.
my God. No.
Does that make sense? How we've simulated this probability? Does it also make sense that in the context of what a simulation does for you, you really couldn't have calculated that probability? You guys would have done 9 times 1.4. That becomes the expected value. That's just the expected value of the number of cars you'll stop out of 9. I wanted to know the probability of catching somebody with drugs before that 9th car. Those are two different things. Okay? Next simulation I want you guys to do, I want you guys to work on this one on your own. Which one do I want? I'll give you this one. A well-known paradox runs as follows. Suppose every couple continues having children until they have a boy, and then they stop. What percentage of male births will result? No couple can have more than one boy, while many can have numerous girls. So it appears that the population will become overwhelmingly female. I want you to test this using simulation, and I want to know what conclusion you reach. Okay? So I need you guys to simulate this. Now, you don't have a random number table. There's one in the back of the book that you can use. However, you do have a calculator. And here's what you can do with the calculator. You're probably going to want to use it for this simulation. You're going to press math, and you're going to go over to PRB. That stands for, shockingly, probability. You're going to go down to the one that says random int, and you can tell this calculator, and we've already talked about seeding the calculator with random numbers. I know we've talked about that. Just tell it the numbers you want to choose between, and it will put it into the hopper and spit out a random number for you. So, you have a choice. If you're looking at males and females, you know that it's 50-50 having a boy or a girl. In your simulation, you can go from 1 to 100. If you wanted to go 1 to 100, and you could say, if it's even, it's a boy. If it's odd, a girl. And that represents having a kid. Okay? If you wanted to, you can go random 1, 2. 1s are boys, 2s are girls. Okay? It's up to you to come up with however way you want to simulate having a kid. But what I want you to do is I want you to run 20 simulations. A simulation in the context of this problem will be one family. Does that make sense? And after you've run the data for 20 families, I want you to give me the probability of boys to girls, or give me the probability of males. Does that make sense? If you keep pushing enter, it'll keep doing it.
Great.
Okay?
The only problem is you can't roll it back up.
No. Just hit it once every time. Is everybody clear?
Yes.
All right, go.